So yeah, this is unSmashing the Stack. My name is Shawn Moyer. I live in St. Louis, and I'm an independent security consultant, recovering Fed as well. So out in private sector, trying to get used to having deadlines, and it's a little bit different. So yeah, like a lot of people in the security industry, I think most of us don't really work in the attack space. We're really in defense. I'm kind of excited that we have this track and this topic area that we can talk about that side of things, because I think most of us, we have to come back from here and try to figure out how to do our jobs. And for a small percentage of us, that's about attack, but for the rest of us, it's about trying to figure out how not to get owned. So I spend a lot of time thinking about that, and most of these talks, when I put things in, they're just sort of something that I haven't heard anybody talk about, and something that that I'm thinking about. So this is kind of the same kind of thing. It's just something that I've been obsessing about. So yeah, I work in incident response a lot of web application security, and lately people are calling me an architect, which basically means I kind of connect lines together on Visio and tell people what they can't do. I think that's what that means. So yeah, so I spent a lot of time staying up all night trying to figure out ways to save the world, and really kind of where this talk came from is about a year ago, about a little more, about a year and a half ago, I was working on a big yellow outbreak for a big multinational, and these guys were just trashed. I mean, their network, we've all been down this road. Their network was down for like 3 days, couldn't do business, everything stopped. And Big Yellow, if you guys are kind of familiar with it, Big Yellow was a stack-based overflow in a network service on the Symantec AV engine. And so these guys were pushing out updates and pushing out SIGs to their AV engine, but they hadn't patched the engine. And it was a known vulnerability, had been around for a while, et cetera, et cetera, et cetera. But I'm sitting there at 4 a.m. I've been up for like 36 hours. And it seems like I end up doing that about 2 or 3 times a year on something. And I'm like, I've been doing this for 10 years. And I don't even know if I can handle another 10 years of the same stuff, and it's the same problem over and over again, like say, buffer overflow in a network service. So, at the time there was a lot of discussion about some of the exploit mitigation stuff in Visual Studio and the GS cookies implementation, and why didn't that help with Big Yellow, and so it really got me thinking about sort of not just looking at what the vendors are telling us or what MS is telling us or anything else about exploit mitigation, but trying to kind of really understand the topic. So yeah, so standard disclaimer, and I think you kind of got that already. Not an exploit developer. Don't speak hex without a converter. This is really my attempt as somebody who works in defense on that side of things to really understand this, and that's really the intent here, is to kind of get that message across to the rest of you guys that do this every day. And I think a lot of these things are sort of understood in the exploit research space and the vulnerability development space, but for the rest of us in the other side of the world, we don't really deal with this every day. So yeah, so one of the things we're going to go through is kind of the Wayback Machine, the history of sort of buffer overflows and network-based exploitation and how it all kind of works. We all know what Lincoln said about history. And then we're going to look at some of the approaches in exploit mitigation. So compile bits, lib bits, kernel bits, approaches to building better integrity in memory and the canary approach. And also what I sort of call let's see if I can get this right, anti-heterogeneity, which is essentially, the intent of ASLR, address-based layout randomization, is to make exploits less repeatable and sort of make things less homogeneous and more diverse, to make sort of mass exploitation a little trickier. Yeah, and then in addition to that, we'll look at some other approaches to containment. Access control models, and then of course static analysis, and then also look at some of the implementations today on sort of the commodity operating systems. So yeah, I mean, I kind of hit on this already. To me, the InfoSec industry, by and large, what do? We patch, we scan, we patch, we scan, we patch, we scan. And the cycles get smaller and smaller and smaller, and the problem gets worse and worse. I remember 3-4 years ago arguing with people that they needed a patch, once a month. Come on, guys, you've got to do it. Once a month, Patch Tuesday. We can't wait another month after that. And now we're getting down to off-cycle updates and things, the cycle accelerating and getting smaller and smaller and smaller and smaller, and it doesn't seem like things are fundamentally improving any. So, to me, a lot of it comes down to what we've done as an industry is sort of retrofit the 80s model of antivirus, which is about patches and exploits for sale on a subscription basis. That's what we're all buying. So it's something that they arrived at in the 80s because it was kind of like selling disposable razors and disposable razor blades. There's a guy, Larry Tippett, who's was the original author of Norton Antivirus, and there's a quote from him that it's easier to detect the 500 things that your system is supposed to do than the 55,000 things that it's not, but there's no profit in that. And that's kind of where I sort of see things. It's kind of this flailing death loop of just updates and patches, and it never seems to get any better. So yeah, it's getting a little old to me. I'm kind of tired of doing it. I don't know if the rest of you are. So exploit mitigation is kind of a different way of looking at the problem, and what can we do to approach it in a little bit different way. So yeah, fundamentally what we're talking about in the case of buffer overflows at a very high level is just corruption of memory space leading to control of execution flow, right? So I think we all know that. The best explanation I ever had was 10 pounds of crap in a 5-pound bag, right? So it's corrupting memory and then leading to execution. And so I had somebody tell me that it had been around since the 40s. We'd understand buffer overflows since the 40s, and I wanted to find verification of that or proof of that, and so I started digging around and trying to get a handle on it. And I didn't find anything quite that far back, but at least as far as the 60s, the expression "Fandango on core" was something from the Algol Fortran guys in the 1960s. They essentially understood this problem all the way back then. So, and this guy's kind of the prime mover. This is von Neumann, and von Neumann was one of the Manhattan Project guys, who also was involved in some of the early system designs of things like UNIVAC. And at the time, in the early systems, the way that you implemented new code was essentially to rewire or resolder. And so what von Neumann came up with is the data encode abstraction. So you have code, that's instructions, and then you have input. And by modularizing those two and being able to kind of feed the input here and then feed the instructions over here, that allows you to essentially rewire every time you launch a new executable, right? So fundamentally what everything has been about since then has been breaking across that membrane and going from the data segment to the code. And then we've got these guys. I always ask, does anybody know who these guys are? Somebody should. Right? Anyone? Bueller? Nobody? Okay. So it's Thompson Thompson and Ritchie. I tried to find a picture of Kernighan and Ritchie, but I couldn't find one of them together. The thing that's kind of interesting about that is that when these guys developed C, this was the computing model. It was the guy at the other teletype that you were dealing with. And so there's no, the bounds checking and sort of thinking about a security model and everything else in that platform, it really wasn't necessary. And so we're still dealing with this code base that was designed with this kind of concept of the computer room. And if you go, a lot of you guys are feds, right? So you go to some old building and they'll say the computer room, right? And they really mean the data center, but it's called the computer room because it was the room where the computer was. And you had the guys that walked into that room and did their work and then came back, right? Obviously things don't work that way now. It's a distributed model and everything's connected together, and we're still kind of approaching our fundamental design to computing with that kind of approach. So yeah, in the age of the dinosaurs, really the first kind of widely exploited buffer overflow was the Morris worm. And if you go back, there's a really good RFC 1135 that talks about it. And then Gene Spafford did some write-ups on it. And what was really funny was it was really just kind of the first wake-up call. All these interconnected systems with network services listening on them, and one sort of bad actor changing the way things work. And so what's funny about it is, Spaff says at the time, the finger D was one of the exploits in the Moyer swarm. It had two payloads. It targeted sendmail and fingerd. And in the case of fingerd, it was because there was a getS call that just took arbitrary input, and then you could just essentially just feed it shellcode. I mean, that's basically what Morris was doing. And so, SPAF in 1988 said, hey, this is a bad idea. We should really be looking at, type-safe languages, and we should really be not using unsafe calls. So yeah, that's, happy 20th birthday to the Clue phone. So that's when it was first really kind of, somebody really put a finer point on it and said, hey, this is the problem. And that's actually bug ID 2 on BugTrack. Bug ID 1 is the sendmail debug bug, which was the other one that was exploited by the Moyer swarm. So I don't know what bug ID we're up to now. I think it's got to be in the thousands. I haven't really looked in a while, but it's all basically that same problem for 20 years now. The same stuff over and over. So really, where people first started really thinking about network-based buffer overflows was about 7 or 8 years later. At the time, if you read some of the early 80s, 90s BugTrack stuff, what you'll see is more like kind of just silly configuration things. Like there was an old Vax bug where you hit enter on login twice and it dropped you to an admin prompt. It's like silly stuff like that. But once we started to get a little better at that, a guy, Thomas Lopatic, who also was the author of some of the earlier IIS exploits and things like that, he stumbled across a buffer overflow in the NCSA HDBD, which was running as root on the public internet. And in his write-up on it, what I thought was kind of cool is that when he figured it out, he said, hey, wait a minute, this looks a lot like the Moyer swarm. This is kind of the same thing. So the difference was, of course, that you had everybody jumping to the web at the time, and all these services that people were lighting up on the public internet. And this is sort of the birth of internet security and us all dealing with this problem. Around the same time, Mudge wrote actually really what I found to be the first paper on buffer overflows. I know a lot of people talk about ALF1. He actually wrote a really brief little thing called How to Write Buffer Overflows, and it defines even today a lot of the same kind of things that still work. So it's shellcode, it's not sleds, and he talked about ways to use GCC to generate your assembler for you and things like that. So that was really what I thought was kind of interesting. It was really the first paper out there on the topic. And then, of course, in '97 we had Smashing the Stack for Fun and Profit, right? So that's kind of the seminal kind of body of work. Something I think that's kind of cool about that now is that if you Google for it, most of the references you find now are for university classes and textbooks. And so now, apparently, in comp sci, you have teachers that are having people kind of run through this as part of a development class. Here's how to write bad code, and here's how to fix it, things like that. So unfortunately, we've had this whole generation of programmers that didn't think that way. So it's going to be a while till all those people kind of come out into the world and the other guys retire, right? So the next kind of major development in this space was actually Solar Designer, who probably most people know as the author of one of the first no exec patches. So the no exec stack patch for the Linux kernel in the early days of exploit mitigation. He was one of the first people to start thinking about this. And what he found was his own patch. He found a way around it. He said, I broke my own stuff. So that's the return to libc. So return to libc attack is basically calling a preloaded function in the payload. So you have a buffer overflow, and in the exploitation of it, in the payload, instead of inserting shellcode, you're actually calling some preloaded library. And the reason it's called return to libc is that typically it's the system call, simply because the system call will allow you to exec a local command. So that didn't execute on the stack, so it still worked without having the ability to execute code on the stack. After that, a couple of years later, you had the woo-woo guys and woo-woo on heap overflows, and this was when we first started to kind of really start thinking about the heap. And that's actually something that I'm going to hit on later when we start talking about some of the exploit mitigation implementations, is that really the heap is still kind of a little bit more of a fuzzy area. It's not as well defined in terms of protection. So everybody's really starting to get a handle on things like no exec stacks. ASLR is kind of becoming more widely adopted, but the heap is still kind of an open frontier right now, I guess. So yeah, NIST remote buffer overflows. And if anybody works for NVD or MITRE or something, your site is broken now for this. I did a search like a year ago and was able to get the '06 stats, and I couldn't generate the same graph this time, so I'll have to check back later. I wanted to get the '07. So yeah, you know, the number's getting bigger, right? It's not getting any better, you know. I think the thing that really kind of clicks for me on this is that we went from, if you look in the you know, in the 80s and 90s, you know, a couple of bugs a year. I remember when I could read bug track, you know, like it actually read it, you know, on a daily basis, and now it's you know, you're just inundated. It hasn't got any better. I think it's, you know, like I said, it's probably got worse. So yeah, so fundamentally, you know, you're talking about unexpected input for an unchecked memory allocation, and then the three targets are the stack, the heap, preloaded functions, and we're essentially just moving the pointer to that payload that's been inserted and then getting control of execution, right? So that's it. At a very high level, that's what we're dealing with. So again, the first approach in exploit mitigation was non-executable stacks. And you know, it's funny. I have a buddy who's a Java developer, and I talked to him about this topic, and he's like, "What? What are you talking about? You know, I don't get it. You know, because to guys that do Java, you know, data and code are all kind of intermixed. You know, because it kind of builds stuff on the stack. But with a non-executable stack, you're basically saying there's portions of the stack that are data, there's portions that are code, and it's attempting to kind of wall up the memory in between the two. So one of the first implementations was the Solaris implementation, which is the no exact, you know, user stack equals 1 bit that you could set in, I think, Etsy system, or you could do, you know, NDD flag to it. I used to do a lot of checkpoint on Solaris and a lot of Solaris hardening, and we used to always kind of congratulate ourselves on this. You know, we're so cool. We've got, you know, no exec stack. We're totally safe. You know, screw everybody else. And we'll get into, you know, some of the problems with that. In the around, I think, what, 04, 05, when you started to see people moving to 64-bit arch on a wider scale with AMD 64 and things like that, you started to see wider adoption of this. And the reason for that is 64-bit platforms have a different kind of paging model than 32-bit. Just to be really dorky, apparently on, what was it, 8088 architecture on Intel, we actually had something similar to this. There was ability to set execute in memory on different things, and they actually took it out because they said, oh, this is inefficient, we don't want to do this. But when you got to 64-bit and you have a different paging model, it makes it possible to take different areas of memory and say, okay, for this section of memory we can execute, for this one we can read and write, but we can't execute, right? So you're schmotting memory if you're a, you know, dorky Unix guy like me. One of the things that's, I think, really important to understand about that is that this is opt-in. The compiler has to be aware of it, the OS has to be aware of it, and you have to flip this bit, which is bit 63. And so you're flipping a bit to execute or not based on flags in your compiler and hooks into the processor. So the proc itself isn't doing anything. And, you know, it's simply got that functionality and the OS is hooking into it. Beyond that, you've got the software emulation. And so MS's dep kind of does both, depending on what platform you're on. Apparently it will hook into the PAE stuff if it's a platform that's PAE capable, and I think like you get this little thing that pops up, you know, in the system settings for it that says, you know, this system has, you know, dep enabled in hardware. Otherwise, what you're doing is a software emulation. And like I said, the first one was the Solar Designer stack patch. After that, obviously the PAX guys, which we're going to talk more about, built a more detailed implementation of it, and then Red Hat has the exec shield stuff. All of these do it in a little bit different way. It's a lot less fine-grained, so you're sort of taking a line in the sand, and so you say, for this upper bound of memory, everything that writes to here can execute. For this area here, everything that writes to here can't execute. So you just have to kind of segment your memory, and that's why you'll hear it kind of being called segment-based as opposed to page-based. So, you know, fundamentally, I kind of use this a lot. You know, functionality breeds exposure. So, with things like virtualization, Java compilers, .NET, all of these things. We have to have the ability to opt out of this because an emulator or virtualization by definition is executing on the stack. That's what it's doing. So the problem is every operating system has to build some little switch you can flip, right? So they have to build a way for you to opt out of the model. So everybody has built in some kind of method for opting out, right, on a sort of a per executable basis. So you have the process execute flags. You have mprotect and virtual protect, which probably want to talk about more. Those are essentially calls in C that you can make that allow you to say, for this section of memory, just leave it alone. You know, sort of laissez-faire. Let me do my thing up here, and I'm going to construct the stack the way I want to do it. And then you also have like the dep exceptions list. The implementation that I've been most interested in looking at this and most impressed with has been obviously PAX. And if anybody is not checked out PAX, go check it out. I'll plug that like 5 other times. But the way that PAX does it is based on a file header. So it's essentially you're flipping a bit in the file itself, and it says for this particular file, it's exempted from this. When you do it at runtime, it's a little more interesting. So the first and most obvious method to getting around a non-executable stack is return to libc. So, you know, like we talked about previously with that, you're essentially calling a preloaded function in memory. One of the other things that you can do is to return to libc, make the mprotect call, and then set a new allocation of memory that can execute on the stack. And it requires, you know, a known address, right? So one of the things about return to libc attacks is that they're usually going to be centered on this particular distribution, this platform, this build, you know, for this version of libc. And when we get to ASLR, we'll talk about some more of that. Heap-based overflows, again, you know, the non-executable stack is like a specific set of criteria. So as long as you don't do it in that exact way, anything else that's outside of that, you can bypass the protection. So heap overflows are something that seems to become of a lot more interest of late because everybody's starting to build things into, you know, with ASLR, they're building things into libraries, and they're starting to build things into the you know, the stack on execution. But the heap is sort of less an area of less focus right now. Peer and post at mbody are a couple of researchers, I think at UMich, that came up with what they call a Hannibal attack. So essentially what you're doing there is you're feeding your shellcode first, or excuse me, you're feeding your function pointer first and moving a pointer to somewhere else, and then you feed your shellcode via an argument at that same address. So what happens is it's not a single payload that just leaped across the stack. So you've done it in 2 different places. So in that case, again, you didn't break out of the model. You still complied with not executing on the stack. That's really what's kind of key. It's sort of one vector. This one was kind of interesting. Escape and Skywing came up with a method to opt out of dep. And so, you know, in the case of dep, what you're doing is you're setting a flag at runtime, you know, in processor that says for this particular piece of code, it has the ability to execute in memory, and then it's enabled disable. So that's that little checkbox you're doing, you know, that says configure dep for all programs or all system services or whatever it is. Well, the problem is you can overwrite that flag. So if part of your payload essentially just becomes a speed bump. So part of your payload is to flip that bit and then execute on the stack, right? Because it's an opt-in kind of thing, it's an opt-out kind of thing, it's software configurable. So the key thing that I took away from that is there's actually, I guess it's kind of quasi undocumented, it's not sort of configurable through the OS itself, but in your boot INI in Windows you can set no execute always on, and that means you can't opt out. The 2 options in the GUI do the same thing because they both do it on a software basis. So if you have, you know, services I select, or, you know, only those services except for these exceptions, both of those mean that it's tunable on a software basis. But if you set it to always on, it does it for everything, and it will crash some stuff, unfortunately. But you know, on a critical Windows box, I would definitely do that. So yeah, so on non-executable stacks, if it's opt-in, if it's an optional security model, it's really not a security model. A lot of these are compiler flags. They're bits that you set in compiler when you build code. You have to hook into the model. And a lot of those things aren't on by default, and they're not terribly well documented. MS actually has done a better job with Visual Studio of trying to build all these things to be on by default, so developers have to go out of their way to disable. Something that I would suggest on any kind of code review process is to make sure that there's some sort of documentation of how that's done and when it's done. And one of the other ones that kind of made me cringe is if you flip the /O flag in Visual Studio, it's the optimized flag, disables all this stuff, because nobody wants to optimize their code. And the same goes for GCC. If you do like 04 or 06, I used to always do the funroll loops in 06 because I was cool like that. That will disable all of the stack protection bits. So yeah, canaries. The way that I think of this stuff is sort of tripwire for the stack, right? So these are a series of extensions to compiler, building a canary value to the return address in the initial case of stackguard, and then if we see a change of the canary, we halt execution. So you kind of stamp the pointer, and as part of that, whenever an exploits payload tries to overwrite the pointer, you check against that and stop. So it's, yeah, to me it's like tripwire. It's the way I sort of think of it. And so the very first implementation was stackguard, and I think a lot of people had at least some exposure to that. What became a lot more widely adopted is ProPolice, and this has been adopted and integrated into GCC 4.1, and then MS's GS extensions have been progressively adopting more and more of this. So the earlier GS extensions just kind of did a little bit of it and just did it for the return address, and now what you're seeing is a lot more integration that's kind of closer to what they're doing in GCC. So ProPolice, they don't really call it a canary, it's a guard value that's stored somewhere off the stack. The thing to me that's more interesting about ProPolice, though, is not so much the canary implementation as much as it is the fact that they've sort of built what Hiroki Ito, the author, calls a well-ordered stack. And so I was wondering what was the police in the in the name of this thing. What did that mean? And what it actually comes from is that ProPolice is something that bees use to construct their hives. And the point of that is it's really about building a better order to the stack, where it's not just sort of arbitrary and somewhat chaotic, but to build kind of order into the system, like the way a bee constructs its hive. So it's actually a pun, I guess, the name of the code. So in that case, what's kind of important, I think, more than just the guard page with ProPolice, is that you're constructing the stack in such a way that the typical targets of an exploit, being the return address or the frame pointer and things like that, usually in the case of buffer overflow, you're either hitting like local variables or arrays, the stuff down there at the bottom. Well, that's growing one direction and the other bits are growing the other way. So in order to get to that, you've got to harm that guard value. So it's about the canary, but it's also about kind of building a better way to construct the stack. And most of the people that I've talked to that do exploit development have said, a well-implemented system with ProPolice is like, it really is kind of a pain in the ass for them to deal with. So that's good. That's what we want, right, on the defense side. Something else in the kind of canary world is heap canaries. And so this is the same kind of concept that you're applying to the stack, but also applying it to heap memory. So it's the same kind of thing. What we're doing is putting guard values around a memory allocation, and we're saying, okay, at this address and that address, if anything changes in that allocation, then we're going to halt execution. OpenBSD has an option for this that's in malloc.conf. It's disabled by default. And the reason for that is that it breaks a lot of stuff. And that's kind of what you see in a lot of things. Probably the most interesting one, I think, is the DL malloc extensions that William Randolph did. These are supposed to be integrated into DL malloc. So it doesn't seem that anybody is shipping with this yet, but it is coming, so that's pretty cool. So this was accepted into DL malloc for integration, so we should be seeing this in libc. So on the GNU-based systems, we will see a actual kind of heap canary implementation. And then there is some of this in Vista in terms of sanity checks and things like that on the heap. But So in attacking canaries, one of the biggest things that we found was StackGuard. Initially, in the case of StackGuard, what you were doing is protecting just specific addresses. So like a classical buffer overflow targets the return address, right? So you overwrite the return pointer. So if you just do a canary for the return pointer, which was the initial StackGuard implementation, there's lots of other things that you can do. You can overwrite the procedure linkage table, you can overwrite the global offset table, you can overwrite stack frame pointers. So the point of it was, of a lot of the attacks against, especially StackGuard, was that you weren't sort of protecting the entire stack, you were just protecting one point of it. So same thing with canaries as with no exec stacks, it just becomes sort of that one vector. So there's so many other places that you can come through. Some guys from Hurt, Bulba, and Killer in Frac 56 talked about the same thing, return address only problems in StackGuard. The other thing that I found kind of interesting that they talked about in there was another paper in Frac talking about abilities to read the canary. So if you have something that discloses memory, if there's any kind of memory disclosure vulnerability that's maybe not exploitable in and of itself, but if you can read the canary value, so it becomes like a multi-stage payload. So you read the canary information and then you insert. So, but what they found was writing over the return address only, as long as you didn't harm that canary value, everything was happy. So if you found, it was a very specific set of circumstances, but if you found a way to write just that part but not touch that canary value. So it's kind of like, I guess, everybody knows about like the MD5 collisions and stuff like that. It's kind of the same sort of thing. You've got to have a very specific case to do it, but it's possible to hit against that. So yeah, so along the same, so we talked a little bit about that. Arbitrary reads to memory, format string bugs, things like that. Any other kind of information leakage that would disclose memory makes it possible to circumvent kind of a canary-based attack. So I said I was going to plug PAX and GRSec a bunch of times, so here I go. In the case of PAX, you have it with GRSec, you have a integration with PAX that allows you to have some additional protections against memory reads, and so you can flip some kernel bits that say, who can read memory, and a lot of that's about protecting ASLR and protecting canaries, because then it makes it more difficult to disclose those addresses. So you're relying on that canary value, so it's like it's like a ciphertext or something that needs to be protected. So yeah, so anti-heterogeneity ASLR. Yeah, the PAX guys were really the first to originate this concept. The userland, the kernel stack, any memory mappings are all randomized with different degrees of randomization based on 32-bit platform, 64-bit. I didn't really want to get into the whole this platform has 32 bits and this has 16 and 24 and stuff like that, because it was kind of silly to me to go through that and give people a report card or something. But PAX does have like the greatest degree of randomization, things like that. And they're a very security-centric project, so they're willing to sacrifice performance a little bit, maybe in a few cases. Although, in some cases, some of these things actually improve performance, especially like the memory allocation stuff with non-executable stack. So the thing that I like a lot about PAX is all these bits are tunable, so you can flip syscontrols and you can say, I want to turn on this function or that function, and you can also tune it on a per binary basis, so you can allow individual binaries to be exempted out of it, but not disable it for the entire system. OpenBSD integrated ASLR with 3.3 and above, and the one thing that they do that probably nobody else does is actually definitely nobody else does, is the stack gap and stack fencing approach. And there's some question about how useful this is, but it's just basically like a small randomized gap in the stack that's sort of shoehorned in at execution time. So it's like, I want to say something like 8 bytes to 4, up and down. And so it just basically, the same thing. It's meant to make return addresses less predictable and the layout of the stack less predictable, so it's tougher to target. And that's what they call stack gap. And they, like I say, they also have ASLR in the heap. And then the exec shield implementation is the Red Hat stuff. So Red Hat, there's some political debate about this. The Red Hat guys kind of decided to build their own implementation and not integrate PAX. And PAX is a lot more mature and has been around a lot longer, and had a lot more scrutiny, I think, than their stuff. There's been a few, well, more than a few specific attacks that have found ways to work around the exec shield stuff. So to me, it's not my preference anyway. In the case of Vista, you have ASLR. That's a big marketing item for them. I talk about in the paper how the PAX guys and the OpenBSD guys probably cringed a little bit because nobody in the IT media knew about ASLR till this did it. They were really pushing this out, that this was going to make a huge difference. Again, it is something that you have to build into your code. You do have to compile against it with /dynamic base flag to Visual Studio, and it is kind of an opt-in model. Did anybody see Ollie Whitehouse's talk here last year? So Ollie Whitehouse did a talk on Vista's ASLR, and especially on the heap, found that there were some problems with the predictability of addresses and that it wasn't quite as strong in randomization on the heap. The understanding I have is that the next service pack is going to increase some of their ASLR capabilities, so it's going to address some of these things. But he's got a really great paper on it, and what's cool about it is essentially what he did was reboot a Vista machine like thousands and thousands of times and graph out the allocations, because one of the things it does is essentially at boot, because it's sort of a monolithic kind of OS, it loads these libraries and everything else at some random address. Well, so he sat down and kind of graphed that out, and you can kind of see how it's a flatter line on the heap than it is in other parts of memory. So it's kind of neat to like visualize it. So OS 10 with Leopard has started to build some of this in. You have randomized libraries at load time, not on the heap, not on the stack. And the understanding I have of this from the different write-ups and discussions about it is that it's some limitations in the mock architecture, right? So fundamentally, there's some pieces that have to be at fixed addresses in order to get things to kind of play nice together in mock. And so the discussion is that, like, to get full ASLR, and we'll talk about this in a little bit, but essentially if it's not a full implementation of it, it's kind of not really useful. In order to do that, they're looking at a couple of years to really get it to the point they want it to be. And until then, it's really just kind of a false sense of security, I think. They're working really hard. I don't want to ding them too much. When I did the same talk at DEF CON. I had a bunch of Apple guys walk up to me and say, because at the time Leopard hadn't shipped, so I really beat them up because Tiger basically had nothing, and they're like, "We know, we're working on it," and so they're starting to catch up on some of these things. So position-independent executables or position-independent code are key to really implementing ASLR. So even if you have randomized libraries and everything at the DLL level and things like that, if your individual executables can't hook into pick or pie, then you still have predictable addresses within the app. They're just offsets, right? But they're there. So one of the big things is to have that integration built in into all your code. And so without that, you're really not nearly as protected as you are if you have sort of full ASLR. So basically, without pick or pie, you've got some defense against things like return to libc, because your system addresses and things like that are less predictable. But within the given exe itself on the stack, those addresses are just at fixed offsets, right? So John Moyer of Ubuntu Harden, so kind of somebody who's working on integrating a lot of this stuff into Ubuntu, says it's with pick and ASLR and libraries that it's 1 and 2 to the power of stack random bits plus mmap random bits. So it's the combination of both the randomization in the stack and the randomization in the executable makes it far more difficult to predict addresses. So on attacking ASLR, Probably the person who has done the most interesting stuff I stumbled across was Shawn, and he's an Israeli cryptographer. And what I think was kind of cool that he did about this was he looked at this and said, well, wait a minute, this is kind of just bad crypto, right? It's just simply making it more difficult to predict addresses. But how brute forceable is it, right? Because it's not that there's only so many addresses on a system that you can load. So he did some initial work with PAX's ASLR on Apache, and on 32-bit with PAX, which has less randomization than 64. What he found was on a forking service that respawns. So every time it starts up, it's going to load another address, right? So you're just kind of playing slot machine. It took him something like 200 seconds to successfully, on a vulnerable service, to successfully exploit it. So it simply takes brute forcing, right? So Vista and also PAX and GRSec have a bit for this. From what I understand in Vista, it's turned on by default that says after so many failed executions to stop. So if you have a forking service that keeps respawning, this will kill it, and that's necessary to prevent brute forcing. Otherwise, it's essentially just a matter of time. And the other one that's of interest to me about that is, what about things like the client side of the browser, where we don't really care how long something takes to run? So if you have an executable, you get onto a machine that's ASLR enabled, and it just keeps respawning, but it's in a user's, like say in a user's browser or in user space, do you really care? Whether it takes you 400 tries or 4, So that's fundamentally one of the things about ASLR is you're relying on obfuscation. So totally unrelated, but something cool that Shawn had is a really interesting paper about return to libc without function calls. And so essentially what he did was do analysis of a system for known kind of reusable bits, little functions, what he called gadgets. And so it's kind of chaining all these little pieces of code together, what he calls sequence chaining all these little pieces of code together to construct something to execute. And so the thing about it is, since it doesn't actually make a function call, it's not sort of an understood class of attack. So just kind of something neat to read. And I actually saw a few people just lately on a vulnerability list that were talking about this, and I think that it's kind of an interesting attack area that nobody's really sort of paid much attention to. So along the same lines, some of the brute forcing stuff, a guy named Ben Hawks at RuxCon last year talked about code access brute forcing in OpenBSD. Same kind of thing, series of unsuccessful reads to gather addresses and then eventually succeed with return to libc. Ollie Whitehouse talked about the varying degrees of randomization in Vista, especially in the heap. So yeah, so cliff notes, right? No exec stacks if they're runtime configurable, if it's a software configurable bit that's in execution, right? So assuming you've got a vulnerable service, which means that you have some access to memory, they're kind of pointless. So like I said, I personally think that the PAX implementation of actually being able to stamp binaries and say, okay, you can execute on stack, you cannot, is probably a little better sort of method. Although there have been some discussions about ways to flip that bit as well. Canaries, bad crypto is not a panacea. It's key that all of the entire memory space is protected. So something that is pretty important is that in the newer Visual Studio, they've done a better implementation of this. The older Visual Studio GS implementation just kind of does just the return address, and that's kind of it. So they've got better with this, and like I said, what ProPolice is doing with the stack layout is really cool. If you run any code with GCC, do fstack protector all, and read up on this stuff. ASLR, same thing. Bad crypto is not a panacea. Any kind of memory disclosure bug will allow you to, anything that can disclose addresses. And in particular, I guess Dave Maynard talked about this a little while ago with the Google toolbar on, I think, Vista, about, if you have other executables that aren't built with ASLR, then you have a way to disclose memory, you have a way to get addresses, right? So if you can get addresses, then you know where to target, right? So it has to be built, it has to be sort of pervasive across the board, and that's kind of the key point with a lot of this stuff. So other ways to approach the problem, we could just kind of fix the code. That would be refreshing, right? I would still I still think that exploit mitigation stuff is worthwhile, simply because I can't always trust every line of code that runs on my system. I'm not somebody who can do full code audits of every single binary and line of source code on my box. If somebody else has the time to do that, then cool, good for them. Lots of commercial stuff in this space. The DHS guys, any DHS guys here? Are you like deep cover? You can't see that, okay. Not really. The DHS folks funded a bunch of source code review of the various open source projects looking for vulnerabilities. And so what's kind of cool about that is they like this massive like $6 or $8 million or whatever that they're paying these guys to do code review, and then basically find buttloads of bugs and things like Bind and Apache and SendMail, right? So that's cool. I like what Ben Laurie said about this, though, which is, that's really great. It'd be really even better if DHS paid people to fix the bugs afterwards. So, that would help too. On static analysis, so Rice's theorem talks about things like Turing tests and says like for a given non-trivial problem set where it's hard to know sort of all the answers to that. The amount of answers to it is not fully predictable, and I like Rumsfeld's corollary to that. So there are known knowns, there are unknown unknowns. So we know what we know. We don't know what we don't know. We don't know. So I think manual review will always be a big part of this, and there's a lot of new stuff in static code analysis, and I know Weld-Pon's going to talk after this, and I think you're going to see a lot more of that as time goes on, and that would be a nice thing to see, is more of this. So access control models are about containment after exploitation. They're not necessarily purely an exploit mitigation thing, but we protect files and devices and inodes. They're another way to contain the exposure. There are varying degrees of complexity. Does anybody run SE Linux and just love it? It's awesome, isn't it? No? Okay. All the major Linux distributions are starting to integrate some of this stuff. AppArmor appears to be gone from what I'm seeing. I know that Crispin Cowan, who was the author, just went to work for Microsoft. So I'm assuming that they're not going to let him support an open source project anymore, just a guess. But you have the mandatory integrity control in Vista. All the BSDs have some kind of implementation, and Leopard has now introduced some sandboxing stuff as well. So rubber meets the road. The PAX guys are really neat, and probably a great place to start is PaxGR SecurityNet and start reading through docs there if you really want to get a good foundation in how this stuff works. It's a great place to start. They really are kind of the reference model for this. So they have page-based execution protection that integrates with the PAE stuff. They also have segmentation-based. They can emulate trampolines, which is what's kind of required for things like JIT compilers and virtualization. They have ASLR in the kernel stack and userland, and lots of happy little configurable bits that you can flip. If you run Ubuntu, there's actually a guy at kernelsec.cr0.org that distributes debs for signed debs and everything for PAX and GRSec integrated kernels. So you can just plug into that and do your happy little apt-get update stuff, and it just kind of works. The Hardened Gen 2 guys are a neat place to look to for a lot of sort of extensive use of exploit mitigation. They do things like build everything with RATS and FlowFinder, and have integration with PAX GRSec and like a couple other access control models. The Ubuntu Hardened project is trying to add more of this stuff on the Linux space, and I haven't seen them kind of get to the point of like, here's an ISO. So I think they're kind of coming along. One of the big problems with all this stuff is it's going to break bad code. And so you'll see a lot of these bug postings for people that are doing SSP integration on GCC and stuff that say, you know, FStack Protector all broke my app, so I just disabled it, you know. And so getting that consistent for an entire distribution is kind of tough. You know, a good place to start would be to go ahead and build a custom kernel and do packs and GRSec. And when I talk to people about this that are working in the attacker space, that seems to be what everybody's doing, is running packs and GRSec. Is that Mr. Itel in the back? No? There's a post on Daily Dave like a while back that says happy birthday to Brad Spengler, who's the author of GRSec, and it's kind of teasing him a little bit too, but saying, you know, all of the you know, black hat people run packs and GRSec on their boxes, so it's kind of neat. OpenBSD was the first to integrate ProPolice. They backported it into GCC 3. They also do, like I mentioned, some of the heap canary stuff. They have WXRX and ASLR. One thing on OpenBSD is that the mprotect call was sort of concluded that that would be an unPOSIX thing to do, so that you can still make the mprotect call. There's also no randomization or no exec in the kernel stack itself. And same thing, that's kind of been a design, I guess, argument on that. My deal would be like, okay, it's cool, it breaks POSIX, but can I just go ahead and flip the bit anyway? You know, just give me the option. FreeBSD, there are a couple other external projects to add SSP to it. They have a very basic NX implementation, that's kind of it. I think that 7, they're starting to do more with it. NetBSD is integrating SSP right now, and they also have a bunch of things that they're taking packs as a reference model and integrating into 4.0, so they're starting to do more of it. I kind of got some grief a while back when I called Vista the least explosive Ford Pinto ever made, and that was totally inappropriate, and I promise I will never do that again. You know, they've started to improve a lot, you know, and they had done a lot of work. One thing I will say is that I think MS is a great test case for static analysis and code review and things like that. They just whacked the living crap out of their code. You know, there's a lot of other things wrong with Vista, but you know, they have progressed a lot. And when you think about the fact that it is, you know, it's a commodity operating system, they have to support code from everybody. That's tough to do. Consistency is very much an issue, and some of the opt-in bits and things like that, they have to flip. What's Crispin doing? So yeah, the AppArmor author is now a security architect at MS. So I think what we might see is better, you know, a better approach to in the access control models and things like that down the road. My expectation is that you'll see something like AppArmor start to kind of materialize later, but I don't think it's going to be for a while. On O3, you have DEP, and depending on whether something's built with GS, cookies, and all that, you have some canaries. The Winus guys, you should go check out, and they're free for home and nonprofit use. I don't know if that means, you know, universities and things like that or whatever, but they are an ASLR implementation for 2K03 and XP. So until they end of life all this stuff, until you have to turn it off, you can go ahead and get a lot of the goodies that are in Vista. So yeah, Waynus.com, cool stuff. So yeah, OS 10 is probably, how many Macs are there here? It's like the cool security guy thing now for some reason. I haven't figured that out. It's got to be a black one though, right? You know, it's so shiny. You know, they're great. You know, they're all clicky and stuff, but they have Bash. That's cool, and I like them. But they've really got a ways to go in some of this stuff. It's just culturally not something that is really a fit for everything else that they've the way they look at things. You have a very sort of rudimentary NX that's an artifact of FreeBSD and Darwin. You have executable heap, and they have started to integrate with Leopard the seatbelt extensions that do sandboxing, things like that. So you have some policy-based stuff that's written in Scheme, and you can start to like sandbox apps. So they've really, from the conversations I had with them, they've really sort of cast their lot with sandboxing and integrity models and access control models instead of ASLR and some of the other parts of the exploit mitigation stuff. And like I mentioned earlier, there's sort of some limitations to how fully they can integrate ASLR based on the mock architecture. So there are some things that probably aren't going to materialize in Leopard for a long time. Does everybody feel safer? You know, ready to go home and not get owned? That would be nice. You know, I think one of the things that always kind of starts to pop up in my head is that it seems like there's the fundamental model is kind of broken, right? So we can't tear that out. There's so much stuff that runs on all of these systems that were built on this kind of concept. I'm kind of excited about Joanna Rakowska was talking about compartmentalized operating systems. So Minix 3, I guess, is sort of a reference model for some of this, that you really have full separation, and it's you know, I think what Plan 9 or something does this. It's kind of building out execution space, driver space, and like the various, you know, ring 1, ring 0, in such a way that they're very much, you know, truly isolated, compartmentalized operating systems. So that would be kind of cool. Academia, where are you? You know, you guys tend to think, well, gee, let's throw some more crypto at it. Maybe that'll fix it. You know, I'd like to see some, you know, some more work in this space from the academic world. You know, actually, Shockum's probably the only guy, you know, that's like doing a whole lot with this. Yeah, the devil's in the details. Legacy support, you know, compatibility and things like that mean that you have to build some opt-in stuff, especially in the consumer OSs. And, you know, thank you for sitting through this. You know, I think defenders really need to understand this stuff more. Like I said, most of us just spend all our time trying to clean up after lots of other, you know, people's messes. And so I had a lot of fun trying to get a handle on this topic. So go read the John Erickson book. It's really great, a good place to start. If you pull up the paper, I've got a whole bunch of other references to all the other kind of things that I digested in getting interested in this. And yeah, think about what's in your stack, what's on your box. You know? Yeah, that's about it. Thanks, everybody. Any questions, comments, bomb threats? Anything?
So one of the things you mentioned, for example, I use OpenBSD and Leopard as an example, is the fact that nprotect still exists because of the breaking deposit model. But even though it does exist because of ASLR, I found in it trying to exploit OpenBSD or Leopard stuff, if the address isn't there for nprotect, you can't really return it in nprotect. And it's the same thing. You can say what you will about the ASLR implementation on Leopard, but I have yet to see a publicly available exploit. I wrote one this morning for my talk this morning,
Okay.
and those addresses are changing literally every time, right?
Right.
So people say a lot of things about, oh, libc, you can run onto the heap attack, but I find that ASLR is much more than a speed bump. Even if there is a way to get around it, people sort of cavalierly say, oh, it's broken, but then they actually don't try to write an exploit, so they don't know how difficult it really is.
Yeah.
So I just wanted to point that out. People are quick to say, oh, there's a small problem here, then they don't produce an exploit that actually, you know, works around that problem.
Yeah, and I mean, and that's what, in general, what I kind of find when I talk to people on the exploit side about this is, you know, all this stuff is about making this sort of an ecosystem that's tougher to exploit, right? So it's the aggregate of a lot of these things. So like a non-executable stack and ASLR and canaries and all this stuff, it just makes it a lot more of a pain in the ass, you know. And that's really the intent, is to make your job just really
Right.
difficult,
I mean,
right?
so one of the last things you can do is you could actually copy, because it's a non-executable, or it's an executable heap on a site, you could do a return to libc attack that copies your stuff onto the heap.
Right.
So if there was a randomized heap, you'd be in heap
Yeah.
level, right? Obviously.
Right, and what I would say too is, like, when I talk about the different, you know, the different platforms, it's really the intent is to, you know, sort of weigh them all against each other, and like say, kind of Paxton use kind of the gold standard on it. So I have to ding, you know, Leopard a little bit, just because it is the least, like they've done the least amount of integration, with that stuff. But it's still, all of it is better than none, right? And it's all, even, just ASLR or something is better than nothing at all. So it all kind of on aggregate hopefully makes us all a little bit better off. So, anything else? Cool. Thank you, guys.